Hi, my name is Jim. Welcome to Op Amps Part 2. And what we're dealing with here is a summing amplifier, both a non-inverting component and an inverting component. And our immediate issue is to find out what the voltage here is, what the voltage is at the non-inverting input terminal of the operational amplifier. Now remember that the input resistance of the op amp is very, very high, so what that means is we do not need to worry about any loading of the op amp here. So we're going to have to use some circuit analysis techniques to do this, and I'm going to solve this in two ways, one using nodal analysis and the other using superposition. And then once we know what this voltage is, via the virtual short, we'll know what this voltage is, and then we can solve this portion of the circuit in a relatively straightforward manner. So our first problem is this. So what I've done here is I've pulled these resistors out and set them up with battery sources so I can kind of analyze it. This is ground and this is the voltage at the non-inverting terminal. And for nodal, I've assigned current directions. I1 flowing in to the node, I2 flowing up, and I3 flowing in. Now you might be thinking that's really kind of a ridiculous thing to do, seeing that one of these currents, at least, possibly two, would be flowing out of the node. But I don't know what direction they're flowing in, and it doesn't really matter because the math is going to make it work anyway. For example, if I'm in my car, it's wintertime, I'm stopped at a red light, and the rear window defogger's on, and I have the blower on, and the headlights on. I don't know if the battery is charging or discharging. Is the battery discharging to help the alternator handle the load of the car? I don't know. So if I were to analyze that circuit, and there's two voltage sources there, the alternator and the battery, I'd have to guess at a current. And then when I work the math out, if I get a negative number, what that simply means is my guess is wrong. So we have that safety factor. Now if we take this circuit and break it down, since all these currents are flowing in, we have a zero here. So the sum of the currents entering a node has to be zero, according to Kirchhoff's voltage law. And what I've done here is I've taken negative 2 volts, and I'm subtracting from it V plus and dividing that by 1.5K. And then I've done the same thing for the middle source and the same thing for the last source. And the reason that the 2 volts and 4 volts and negative 1 volt, I'll say that again, negative 2 volts plus 4 volts, negative 1 volt, is on the left side of this before this subtract operation, is because of the current directions that I've chosen. Now to solve it this way means that I would have to separate this here, negative 2 over 1.5K, negative V plus over 1.5K, and do that for every single one of these. So I'm going to end up with 6 terms on the right side of the equal sign. Then I would combine like terms, and with regarding the V plus, they all would have different denominators. I'd have to find a common denominator, and once I do that, I can pull V plus over to the left side and solve the problem. But it's probably easier to convert these voltage sources into current sources. And then all we have to do basically is add the current sources together and then find the total resistance of 3 parallel resistors. So that's a Norton equivalent circuit, and that's what I've chose to do here. So we'll take the first guy, this, and converting that into a current source is what I would do, would short this side, and these sources are not active, not in the circuit right now, I'm just worrying about this one. Short this guy to here and find out what the current flow would be from the battery and assign that current to the current source. Now notice I have the arrow going down, which corresponds to the positive side of the battery being connected to ground. Then I take the internal resistance of this source, which I'm treating as 1.5K, and put it in parallel with the source. Secondly, I would Norton equivalent circuit this guy. This time the current direction is going to be up because the positive terminal is away from ground. And then again, to find out the magnitude of the current, is I would just take this top of this 500 ohm resistor here and short it to ground, not paying attention to anything else, and in so doing find out that this is going to be providing 8 milliamperes. And then for the internal resistance of the current source, it would simply be 500 ohms. So you have to remember when we're doing this is that externally you cannot determine if this is going to be a voltage source in series with a resistor or a current source in parallel with a resistor. There's nothing you can do outside of the containers that you can't see into a box to find out if it's a voltage source or a current source. So I did the same thing with this guy and noticed that the current direction flow is down because of the plus side. And then I'm going to be combining things, and the easiest one to combine, of course, would be the currents. So the combination of this would simply be, I guess I didn't even put it on here, negative 1.33 plus 8 minus 1 milliampere, and that would produce a current flow in this direction for our combined current sources of 5.66 milliamperes. Next, what I see is that I have 3 resistors in parallel, and I have to find the total resistance of this for the total current source. And before I go on, I don't want to lose this thought. Remember that you can put current sources in parallel that have different current ratings. You can put voltage sources in series that have different voltage ratings. You cannot put voltage sources, without the resistors, in parallel if they're not exactly the same voltage and exactly the same polarity. You cannot put current sources in series, that's without their internal resistance, unless they're exactly the same value in exactly the same direction. Having said that, the matter of combining these 3 resistors, which you can see are in parallel, I'll use the general formula for this here. And this is derived, of course, from the conductance, which would be 1 divided by RT equals 1 over R1 plus 1 over R2 plus 1 over R3. And in terms of conductance, that would be G total equals G1 plus G2 plus G3. And that's what the basis of this formula is based upon. Now, you can enter this on one line in your calculators using the -1 operation, raising to the -1 power if you're very, very careful. Now, I've elected to break this down a little bit, so our total is going to be the reciprocal of, in the denominator, 1 over 1.5K plus 1 over 500 ohms plus 1 over 1K ohms. And then working it out, I find a total resistance of 272 ohms. So I'm going to put that across my current source. So basically, if we were to look into this, what we would see with the voltage sources, the internal resistance is 0 ohms, would be a 272 ohm resistor. Now I'm in perfect condition here to determine what this voltage is. And once I know that, things get easier. So it's not too hard. V plus is not loaded by the operational amplifier, so all I have to do is to push this current through its parallel equivalent resistor here, RT. And when I do that, I find out that the top of this here has a voltage of 1.54 volts. So that would be this voltage right here is 1.54 volts. So I'm fairly well on the way to solving the problem. So let's take a look at what happens next. Now, to make the diagram a bit simpler, I've excluded all the resistors on the bottom. What we have is the result, which we're interested in, is 1.54 volts. And then by virtue of a virtual short, I can say that this point is 1.54 volts, and all I have to do is find the current flow. Once I know that, all I have to do is push it through the 4K resistor, being careful to anchor it, and I'm going to have my output voltage. So let's do that here. What is this current going to be? Well, we're 1.54 volts, and over here we have -2 volts, so the voltage drop across the resistor is going to be 1.54 minus a -2 volts divided by the resistance, which is 2K, which comes out to be 1.77 milliamperes flowing in this direction. Next, I'm going to find the voltage drop across the 4K resistor, and the same current has to flow, so that's going to give me a polarity of plus to minus. And I highly recommend, when you're solving these problems, that you write down these polarities. Put them on paper. You know, keep them in your mind where you can make a mistake later, have them written down. So, in pushing that current through the 4.K resistor, is what we end up with here is 7.08 volts. So, again, coming up with a diagram which is a little bit simpler than this, all I have now is the voltage at this point, which is 1.54, along with the drop across RF, which is 7.08 volts. And what I know about that is this side of the resistor is going to be more positive than this side by 7.08 volts. This side is 1.54 volts, so V out is simply going to be the sum of these two, which comes out to be 8.627 volts. So with all those inputs, all four of them on the previous page, that would be the answer that we would be expecting to see with DC input sources. Now, with AC inputs, say microphones or audio sources or whatever, we could also solve that. And just for reference, suppose then instead of using the DC voltages, we let that be the peak of the input voltage. And using sinusoids is you can actually figure out what the output voltage is going to be, and by using what I refer to as the attenuation factor, which I'm not going to discuss here, is you can determine what the effective AC output voltage would be. I'm not saying RMS. Effective also means DC equivalent, but let's not concern ourselves with that right now. Okay, let's take a look at superposition here. And what I'm working on are the resistors on the non-inverting terminal. And in superposition, a circuit has to be linear. What I'm going to do is let one source be active and then figure out what the voltage of that source is as a partial solution, and then do that 3 times, add everything up, and it should work out to be the same voltage as what we had before. So I'm going to start here with -2 volts, and what I've done is I've replaced these voltage sources by their internal resistance, which is 0 ohms. So effectively what I have is these two resistors in parallel, and the voltage source is going to be in series with 1.5K. So to find the voltage at this point, and note that these two parallel resistors connect to ground, that means that these guys are going to be in the numerator, and it's just voltage divider after that. So the voltage partial response for -2 volts is going to be -2 volts. In the numerator, these two resistors, 500K in parallel with 1K. In the denominator, the sum total of everything, which is the two resistors in parallel plus 1.5K. So putting some numbers to this, it's a -2 volts. The numerator comes out to be 333 ohms. And a sanity check on that is that this is less than the lowest resistor that's in parallel. Then in the denominator, all I'm going to do is take that value and add in 1.5K, and then the contribution to the total voltage at V plus here for the -2 volt source is a -364 millivolts. 1 down, 2 to go. Next, we're going to let the 4 volts be active and replace the internal resistance of the 2 other sources by a short circuit. What we have is 1.5K in parallel with 1K. That goes in the numerator. And in the denominator, we have that value plus 500 ohms. Again, voltage divider. So the contribution of the 4 volt supply to this is 2.18 volts. So we have 2 partials and we have 1 more to go here. So we'll let the third source, let's see here, -1 volt be active. Like that, and the polarity of this here is showing the positive side is ground, and hence this is negative. And the same is true here. So I'm not calling this -1 volt, I'm letting these supplies polarities say that it's -1 volt. Numerator, same deal, 500 ohms in parallel with 1.5K. And then in the denominator, oops, forgot that guy there. What we have is that quantity added to 1K, and we find that the contribution of the -1 volt supply is a -272 millivolts. So we have 3 partial solutions here, and since it's a linear circuit, all we have to do is add them together, and in so doing, what we come out with is V plus. That's going to be at the non-inverting input of the op-amp is 1.544 volts, which is, for all practical purposes, exactly the same as what we had before. Now, I'm not going to take this any further because the analysis would be the same as on the previous pages. So this is the hard part, is to get this guy done, and I've used nodal and superposition to figure that out. And if you're a fan of mesh, you know, you can use that too. That works fine. Okay, our last configuration is a little bit strange. We have a resistor in the feedback path, and sometimes you see these circuits pop up. I saw one in a medical device not too long ago. And the good news about this, as far as analysis is concerned, is that the non-inverting input is grounded, so via virtual short, we have a 0 volts here, which is going to make our life easy. If we didn't have 0 volts here, well, so what? Virtual short, we just put that voltage here and figure it out. And the first thing we need to do is to determine the current, direction, and magnitude with regard to this node. So what I see here is 2 volts on the left and 0 volts on the right. So conventional current is going to flow in this direction, and that current is going to be 2 volts minus 0 volts, just being thorough, divided by 1K, which equals 2 milliamperes. So since the input resistance of the op-amp is very high, we're going to say that that current has to flow through the feedback path. And once again, remember that this is an analysis technique. Actually, what happens is VID is amplified by the gain of the amplifier, and through the feedback method, we get the output voltage. But for analysis, this is perfectly fine to do this. Anyway, continuing, let us find the voltage drop across the 1.5K resistor, and once we know that, is the problem we have basically kind of falls apart. So that drop, DROP, is 2 milliamperes times 1.5K equals 3 volts. So what we have here is a 3 volt drop, and if we want to find out what the voltage here is at node VX, we see that this 3 volts is anchored on this side, and since the current is flowing in this direction, we can say that the right side of the resistor is 3 volts more negative than the left side. The left side's at 0, so Vx in this case is going to be equal to a negative 3 volts. Okay, knowing that, we can find the current through the 3K resistor, and what we want to do here is combine this current with this current and push him through the 2K, and then we'll be in position to figure out what V out is. So the current flow through the 3K is relatively straightforward, and I put absolute value signs in here so I don't end up with any negative currents. the direction of the current I have on the schematic and the diagram here, so I don't have to confuse myself with signs. And that's going to be equal to 3 volts, negative 3 volts divided by 3K. So we're going to have 1 milliamp here flowing up through the 3K resistor. Now note that this is negative 3 volts. In ground, 0 volts is more positive than negative 3 volts. Hence the current is going to be in this direction. Finally, we can find the voltage drop across the 2K resistor, and our total current flowing into it is going to be 2 mils here, 1 mil here, equals 3 mils through the 2K resistor. And that voltage drop is going to be 6 volts. So we have a 6 volt drop across this. Now, assigning polarities, as in good idea, this is going to be plus to minus, which means that the right side of the resistor is going to be 6 volts more negative than the left side of the resistor. The left side of the resistor is at negative 3 volts. So if we take that into consideration, we have negative 3 plus a negative 6 is going to be equal to a negative 9 volts. So the output of this particular circuit, given 2 volts in, would be negative 9 output, and the gain of the circuit then would be negative 4.5, and the negative again means that it's going to be an inverting amplifier configuration. So one other little issue here, and this is kind of an interesting aside. Question is, what impedance or resistance does the source voltage see if Vn equals 0 volts? So if we had grounded this input and it was 0 volts, what we would be seeing as far as the source would be seeing as far as the resistance would be is that V plus is 0, so by virtual short, V1 would also be 0 volts, and the resistance then would be 2 volts minus 0 volts divided by 2 milliamperes, which would be this current, equals 1K. So that may not seem too exciting. 0 volts here, 1K obviously would be the resistance that the source sees. Now suppose that we let V plus here, our non-inverting input, be equal to plus 2 volts. What resistance would it see? Well, let's find out what the current is. And the current through the resistor here, now this is going to be 2 volts. So this will be 2 volts minus 2 volts divided by 1K equals 0 milliamperes. So the resistance, using Ohm's law, is going to be voltage divided by current, and this would be the resistance that the source sees. And what we have here is a 0 milliamperes in the denominator, which gives us an undefined. Now if we take the limit of this guy, what we end up with is it looks like infinity. In other words, an open circuit. So there is no loading on the source if we make this voltage exactly the same as the source voltage. Now that might be easy to do with static DC voltages here, but not so much if we're dealing with real world signals. And in the last case, I put a plus 4 volts here, and what basically happens is that the current flows in the opposite direction. So this will be plus 4, this is 2 volts, and we would be feeding the source physical current in this direction. So if this were to be a rechargeable battery, say, we'd be recharging it. In this case, of this being 0 volts, we would be discharging it. So that'll do it, and kind of what this says is that the input resistance of this circuit, if V on the non-inverting input terminal is variable, the input resistance is also variable. The source can be supplying current, it can be supplying 0 current, or it can be sinking current. Depends on what this is. So that'll conclude with op amps, and thank you for watching.